Greetings everyone, welcome back into Calc 2. Time to continue and finish our discussion on Taylor series, Maclaurin series, Taylor's theorem. So what we left off was things that we could use the Taylor series for. And one of the main ones that comes up immediately is approximation. Being able to take complicated functions and turn them into a string of polynomials does make it extremely easy to plug in values to try and approximate a more complicated value. So let's start with Taylor's theorem, the actual thing that brings about the Taylor series, and let's talk about how this can be manipulated into exactly what we want, molded into what we want is a better way of putting it. So here's the gist of Taylor's theorem. It says that if you have some polynomial, Taylor polynomial list up to k, okay, then we call that P sub k of x, centered at C. But notice I didn't go all the way to infinity with that. That's a Taylor polynomial up to some n equals k term. The leftover remnant of whatever else needs to be added to make it equal and not approximate, okay, we call that the remainder, and I'm going to label it r sub k, the remainder after the n equals k number of terms, okay, and yes, it is also a function of x. Now the theorem continues to state that after you see this structure, the remainder is formed by taking the k plus 1 derivative of f and evaluating it at some value z divided by k plus 1 factorial x minus c to the k plus 1. So, of course, you recognize the structure here. It's just like building a Taylor polynomial term. It looks like it's the next term, doesn't it? Except there's one major difference. Z is not equal to c, or not all the time. Okay, it's not guaranteed. In fact, z is going to be some value in between whatever x you pick and the c value, the center of your series. So in other words, z is going to shift a little bit depending on what x value you pick. There will be an interval between the x value that you pick to plug into your function and c, which is the center of what you've centered your series around. Okay, there will be an interval in there, and some number in there will be what you're plugging into whatever this k plus 1 derivative of your function is. Okay, now this seems foreign. I can see where that would feel a little bit off-putting, but you actually have seen a very simplistic version of this theorem before. The mean value theorem looks like this. F of x is equal to f of b plus f prime of z times x minus b. Or if you want, we could put c here, so it would be kind of like what you're talking about. C and c. This was mean value theorem. It was written in another way originally, where you had f of x minus f of c over x minus c. It was just an average rate of change, okay? But notice, this is exactly what this is saying. I have the Taylor polynomial, but it's to the n equals 0, plus the next derivative evaluated at some z, and z is just going to be in between x and c. It's in the interval that the mean value theorem talks about, okay? So this is really just a generalization of that same idea, but further down to whatever derivative it is that you cut off in your Taylor series, in your Taylor polynomial. So I don't actually have a series for this remainder part. I'm not adding more things that are plugging in the c into your derivative. I have one term here that sort of fills in the rest of the gap to make this equals, not approximate. Okay, now the thing about this remainder is you have to know what that z value is, and a lot of times it would be extremely difficult to find that z value. So what do we do then in order to make our approximations accurate? Well, it wouldn't be called approximations if we could do them exactly, right? So we won't be finding the z value. Instead, what we'll do is we'll mold this a little bit more generically to fit our situation. We're doing approximations, which means we expect some error. And what we're going to do is have a boundary on that error. And if we understand how to use the boundary, the bounding, the binding of that error, then we can make our approximations efficient. Okay? The error is going to be the absolute value of whatever r sub k is. Okay? So in other words, if you pick a certain level of Taylor polynomial, let's say you pick, I'm going to do p sub 7, then the absolute value of r sub 7 evaluated at your x is going to be the error for p sub 7. Okay? Now, r sub k is going to be equal to this, where I'm finding the k plus 1 factorial, the k plus 1 power of the x minus c, and the k plus 1 derivative at z. The k plus 1 factorial and the x minus c to the k plus 1, those can't be manipulated. Those are pretty much solid fact of whatever your series has been built to be. Okay? So the k plus 1 factorial, the x minus c, those are, you're going to see, they appear right here. Right? You'll notice it's in absolute values, though, because I'm doing the absolute value of the r sub k. But here's the big difference. This right here says to use the max of the absolute value of the k plus 1 derivative of f evaluated at z. Now what this really means is not necessarily finding the maximum z, right? Because z is in an interval. I don't mean shove all the way to the right of the interval and say just take the maximum z. No. What we're saying is, regardless of what z is, to make this work, z is in an interval between x and c. All right? So whichever one's bigger, could be c to x, could be x to c, doesn't matter. Okay? Somewhere in that interval, your k plus 1 derivative of your function will hit a maximum value. Because since it's a differentiable function, right? It's going to be continuous on the interval between x and c. It's fitting into this theorem, okay? And that being said, it's going to be in a closed interval, and guaranteed in Calc 1, if you have a continuous function on a closed interval, it will reach a maximum, okay? So there is a maximum output value for this derivative, all right? Whatever derivative this is, there's a maximum output level between x and c. Somewhere in between, somewhere in that interval where we're picking z from. And I don't care what the z is. Just find whatever that maximum output is, and that's what goes here. And that's why this changes to a less than. Because my actual remainder is just some value in between x and c, right? Whereas I'm picking the maximum. So either I'm equal because my z already is the maximum, or I'm going to be less because whatever z I picked gave out something, less. More than likely it's the less. Okay, but notice what we have here now. By changing this to using the maximum, it's usually pretty easy to just look at something and say, oh, it's decreasing, oh, it's sine or cosine, oh, it's something that I recognize, and I know that it has a maximum of blah, 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 right? You can find a maximum output a lot easier than it would be to solve for the z that would give you the exact value. So then, saying that the r absolute value, the r sub k here, the error is less than some calculation, makes this calculation an upper bound for the error. In other words, you can have some error, but it won't be more than this. Okay? So basically, we've capped the amount of error possible, so we can actually determine a region of how close we are to our approximation. And vice versa, in some cases, I can reverse this around and say, how many terms do I need to go to in order to get this much accuracy guaranteed, right? It's a certain amount. And remember, we did this back with series when we were talking about normal convergent series. We did this with alternating series. We did it with some of the integrating series as well. Okay, it's the same idea, but Taylor's theorem just approaches it this way. Okay, so let's get an example in here of using this. Approximate the cube root of 7 using P3 of x from a Taylor series of the cube root of x centered at 8. Now, let's think about this for a second. Why specifically did I pick that function with that center? Well, the choice of the function should be obvious, right? Because I'm doing cube root. But then why c equals 8? Well, the cube root of 8 is a straightforward integer value. It's 2. And 8 is really close to 7, so I'm pretty sure that if I can get a Taylor series centered around 8, that my interval of convergence will encompass at least up to 7, hopefully, right? Okay, so let's go about building the Taylor series first. There's a couple of different ways you can do this. From the last lecture, we can do it the straightforward way where I list out the derivatives, plug in the values, and set out the series. Or I can try to turn this into one of my recognized structures. Okay? I'm going to choose the latter. Right here, I'm going to say the cube root of x is equal to the cube root of 8 plus x minus 8. Now remember, I'm trying to center around 8, right? So right here, if I do x minus 8, that's centering around 8. So I just did plus 8 minus 8 to make that happen. And it's starting to look like one of our binomial setups. Remember, I need a 1 right here in order to do that. Okay, so then I'm going to factor out an 8, like so. That'll give me 1 plus 1 over 8 times x minus 8, like this. Okay, one last step. I'm going to go ahead and simplify this and write it as a binomial to a power. The cube root of the 8 is now possible because this is multiplication. So it's really just 2 times 1 plus 1 over 8 times x minus 8 raised to the 1/3 power. Okay, so now we have something that's set up as a binomial, and I can list out that series. So this is going to be equal to 2 times, now remember, we're only needing to go to P3, right? So that's going to be 0, 1, 2, and 3, 4 terms. Okay, because the 3 doesn't represent the number of terms. The 3 represents the n value that we're going to. Okay? Now, I've got my first term as 1 plus k times x, right? But k times whatever this is, my k value is 1 over 3. So I've got 1 over 3 times 1 over 8 x minus 8. You know what? I want to switch to brackets right here. Let's make it a little bit less confusing there. Okay. Plus k times k minus 1 times I'm trying to think of which is the best way to write this. X minus 8 squared over 8 squared. Remember the 8 and the x minus 8, that's part of the whole thing that I brought over that's being raised to that power. Okay, plus, oh, I forgot my factorial. This is the 2 term, so I got to do 1 over 2 factorial. Technically 0 factorial, 1 factorial, right? 1 over 2 factorial. So I'll do times 1 over 2. One more term. I got to do 1 over 3 factorial. So that's 1 over 6. And then k, so 1/3. K minus 1. K minus 2 is negative 5/3. And then I'll have x minus 8 cubed over 8 cubed. Okay? So right here, actually, I should switch. Because I didn't go to infinity here, I am now approximating. Because I switched from the binomial function to the Taylor polynomial, right? This is just a Taylor polynomial because I cut off. So technically this is the generic version of our P3 of x here. Okay, now that is going to be equal to 2 times 1 plus, let's see what I have. I have x minus 8. X minus 8 over 24 plus minus, right? So minus, I've got the 1/2 and the 2 reduce right there. So I've got x minus 8 squared over, that's going to be 24 squared. That's fun, right? Okay, plus, and then yes, I actually have the plus here on that one because of the double negative here. Anyway, so let's see, I've got the 3 3s and the 3 8s. That's going to give me a 24 cubed here. I still have my x minus 8 cubed here. And what else do I have? I have the 2 times 5. 5 over 3. Yeah, let's reduce that. 5 over 3. Like that. Okay. Like that. Yes. Okay, so now what I'm going to do is actually approximate the cube root of 7. Okay, so the cube root of 7 is approximately. And then basically all I'm doing is plugging 7 into my function here, right? Cube root of 7 here. But by plugging 7 into that, it's approximately equal to plugging 7 into this. So it's going to be approximately equal to 2 times 1. 7 minus 8 is -1. So -1 over 24, right? And here again, 7 minus 8 is -1, but squared. So I've got minus 1 over 24 squared there now. Okay. And then 7 minus 8, but then cubed is going to give me -1 again. And then I'll have 5 over 3 times 24 cubed. Like so. Okay. So then what is this equal to? This calculation is equal to 1.912953318-ish. And I would label this as P3 of 7. Right? So here's my approximation of the cube root of 7. Okay? Now, to preface this, just so that you can see, I looked up the actual cube root of 7. I didn't just punch it in the calculator. Looked it up on Wolfram Alpha. The cube root of 7 is actually 1.9121182772389, and there's more digits, but that's good enough. Okay, so you can get the idea here, right? So how close were we, right? 9129, right? And then it deviates. Not too bad for only a 4-term approximation, okay? Not too bad, especially like for a lot of the applications we use around the house or in small jobs, right? 4 decimal places a lot of times is pretty decent. But I'd probably eventually want to start talking about more, especially if I was going to apply this to some bigger theorem or something like that. Okay, so now let's use Taylor's theorem with remainders to talk about the boundary of the error and state the accuracy interval. Okay, so my error is going to be based on the maximum value of the k+1 derivative of our function, right? Okay, so that means I need to find that derivative first. My function, f of x equals the cube root of x. So let's start there. F is x to the 1/3. So f prime is 1/3 x to the negative 2/3. F double prime is going to be negative 2/9 x to the negative 5/3. F triple prime is going to be 10/27 x to the negative 8/3. And these multiplications should start to look a little familiar, right? It was a lot of the things that were coming up as we were building our series here as well. Technically, this is the other way I could have built the series, right? I could have done the derivatives and plugged in 8 into each one of these, and it would have given me the coefficients here. Okay, I need one more derivative because we went to P3, so I need k+1 derivative. So I need the 4th derivative of our function, f4. Okay, that's going to give me negative 80 over 81 x to the negative 11/3. Okay, that right there is going to be the derivative in question. Now, for my r sub k value, the actual value, the equals value of r sub k, is going to pick some z, right, in between x and c. Okay? Now, in our particular problem, the x value that we're picking is 7, and my c value is 8. Okay? So for this right here, the z that we're going to pick is got to be somewhere between 7 and 8. Okay? That's between our x value and our c value for our series. Well, if you look at the function right here, okay, this function right here is a straightforward one-term x with a power, okay? This function right here, 11/3 is bigger than 1. And technically, since it's negative, the x is in the denominator, okay? Think about it. As x gets bigger, 11/3 power makes it even bigger, okay? By itself, x to the 11/3 is an increasing function. If you put that in the denominator is increasing as x increases. Therefore, the whole fraction decreases, okay? So this function right here, this is decreasing on the interval where x is somewhere between 7 and 8. Okay? There are no values that I could plug into x here that would just magically make it stop decreasing. X is going to be, a constant flow of numbers from 7 to 8. And the bigger it gets, the bigger this exponent gets as well, the bigger the denominator is going to get. This is going to be decreasing, I should say, in size. Sorry, I should qualify that. The actual value, right, since it's negative, it's going to get smaller negative, so technically it's increasing, okay? If you want to look at the listing of the terms. But it's decreasing in size, so just ignore the negative, because remember, I'm interested in the absolute value of the derivative here, okay? So I don't care what my actual z value is. The max possible of the 4th derivative of f evaluated at any z is going to be equal to the 4th derivative of f evaluated at 7, okay? Let's go through that one more time here. Because this interval from 7 to 8, right, x just keeps getting larger between 7 and 8, then the x to the 11 thirds is going to keep getting larger, but it's in the denominator because of the negative power. So the size of this is going to decrease constantly. Now, since it's decreasing constantly, I have to pick the largest possible. That means I'm going to pick the smallest possible x. It's going to be the largest output value for that derivative. Okay? So that means this is equal to negative 80 over 81 times 7 to the negative 11 thirds. Okay? So that's my maximum output of the fourth derivative there. Okay, so let's set this up to what I actually am interested in finding out here. Let's separate that off right here. My r sub 4 evaluated at 7 error is going to be less than or equal to the negative 80 over 81 times 7 to the negative 11 thirds divided by 4 factorial times the absolute value of 7 minus 8 to the 4, right? To the k plus 1, to the 4 here. I'm sorry, this should be R3. Because technically our n, right, our k value was 3. So that's why I'm getting 4s here for these, and that's the fourth derivative evaluated at 7 there. Okay, so then this is telling me that my error has got to be less than R3 of 7, absolute value, is less than or equal to, when you punch this up, you get 0.00032786942. It's very important that you notice the 4 zeros in between the decimal and the first major digit, right? Notice up here our approximation had exactly 4 digits in common, and then it started being a little bit off. So right here, this error is exactly showing that. I am within this much accuracy, okay? And then my actual error, if you'll notice, is not the same as the 3 would be here. My actual error is something smaller than a 2 in that particular place value. Smaller than 2 because, you know, there's other digits after. However, this is exactly a true statement. My actual error is less than this much. Okay? So that's the beginning right here. What's the boundary of the error? There it is. That's the maximum error I can expect out of this approximation. Maybe I didn't know, you know, this other thing to compare it to. I'm just showing you all that so that you can see how this all lines up. Okay? Now, what's the accuracy interval? To do the accuracy interval, okay, I'm just going to note that the cube root of 7 is going to be somewhere in between our P3 approximation minus my error all the way up to P3 plus my maximum error. Should be max error. Okay, that's what I mean by the accuracy interval. So if you take the P3 of 7 that we found, and I subtract this from it, that's how far down it could go. And if I take this approximation and add this error, that's how high it could go. Okay? The error is a certain amount. It's kind of like a radius. The error is like, well, it's not more than this much away, but it could be this side, it could be this side. But it won't be more in size. So what I do is I just take this as a radius in both the positive and negative directions from this number. And that gives me an interval where the actual value, the true value of the cube root of 7 is somewhere in between those two. Okay, so here's what I mean. Here's the accuracy interval that we're talking about here. If I do P3 minus this number here, so the 1.91295 minus this is going to give me 1.91290531 is the lower boundary for where the cube root of 7 could be. And then the P3 plus this maximum error is the 1.912986,105. That's the accuracy interval that I'm talking about there. This is the interval where the actual true value of the cube root of 7 is somewhere in there. Okay? It's somewhere in there. And obviously those first 4 digits are smack on. Okay? And the true value, you notice, is actually just a little bit bigger than this, right? It has the 3 there instead. So it's just a little bit bigger. Okay? So that's one way that we can use this error bounding to help us see how efficient our approximations are. If you have an approximation, you can ask how efficient that is. Okay? In the next scene, we'll reverse the question and say, how could I get this much accuracy? But here, this is how accurate is this, right? Where am I at with my accuracy? So you can say you have at most this much error, or you can say you're somewhere in this region, right? It's kind of like zooming in, right? Your interval could have been big, but now we've gotten it approximated to here, to this interval. And the more terms you add in, the interval will continue to shrink because your error will shrink. So we just saw how we can put a boundary on the amount of error that we're getting from the series approximation. Let's talk about going it from the other direction and saying, if I have a certain amount of accuracy that I need to have, how can I guarantee, how many terms do I need to guarantee that level of accuracy that I'm requiring? Okay, so that's this kind of question, right? So how many terms of this power series, of this Taylor series, are required to approximate the ln of 1.6 to within 0.0000001, right? That's 7 zeros and a 1, by the way. Okay, 8 decimal places down. That much accuracy, okay? Which, by the way, is the typical accuracy that you see on a lot of different calculator displays, give or take, right? Close to it. So how many terms would we actually have to sum up so that I could guarantee that it is less than that far away, right? So in other words, I want my error to be less than this, right? Okay. So then, where we're going to start is by building the error term in general, right? Okay, so my error term, don't forget, comes from the absolute value of the r sub k of x, and that's equal to the function k plus 1 derivative evaluated at some z value divided by n factorial times the absolute value of the x minus c to the k plus 1 power. And I messed up here. This is the k plus 1 factorial, my bad. I have the other one in my mind for some reason. Right. Okay. Now that's what the error term is equal to, right? I want to make sure that my error term is less than this. So at some point, I'm going to want to say that this calculation is less than this number. And hopefully that allows me to solve for some value of k that I can get to saying, oh, I need this many terms. Okay, I need to go to this particular level of approximation, this particular value of n and k. So let's start with the derivatives so that I can make a pattern out of this, right? Because right now this isn't really in a solvable setup. This is just a structure for building individual terms. If I could make some sort of patterned object that I could put here that has to do with k, z, x, c, whatever, okay? Let's start with the derivatives. So my function f is the ln. His first derivative is going to be 1 over x. The second derivative of that is going to be negative 1 over x squared. Third derivative, we're going to have 2 over x to the third, right? Because negative 2 times negative 1. Fourth derivative is going to be negative 6 over x to the fourth. Fifth derivative is going to be 24x to the fifth, or over x to the fifth. Let's do one more. The sixth derivative here is going to be negative 120 over x to the sixth. Okay, so with these derivatives, there is actually a pattern here. Notice it's staying as the fraction the whole time, right? And then every time I'm just multiplying that new power. The signs are going to alternate, positive, negative, positive, negative, positive, negative. The exponent on the x always matches the level of derivative that I'm at. And the numbers multiplied in the top are just multiplying 2, 3, 4, 5, right? 2 times 1, then times 3, then times 4, then times 5. That's factorial. Okay? So it looks to me like right here, the f sub nth derivative of our x, whatever value it happens to be, is going to be negative 1 to the n plus 1, because the first derivative there is positive. And then n factorial, n minus 1 factorial, over x to the n, right? Because this is 5 factorial, but it's the 6th derivative. 4 factorial, but it's the 5th derivative. That's why it's n minus 1 factorial. Okay, so I've got a pattern for my nth derivative. That means that I can set up a calculation for my error now, right? So my error, r sub k of x, is going to be equal to, and actually, it's not just of some generic x, is it? It's actually of 1.6. So let's go ahead and say that. 1.6, because it's going to be my error term of this x value. That's going to be equal to the absolute value, negative 1 to the n plus 1. That's going to wipe out because of the absolute value anyway. Now, what we have here is we're actually doing the k plus 1 derivative. So technically this should be n plus 1 plus 1. Okay? This is going to be k plus 1 minus 1. So it's k factorial. Okay? Divided by x to the k plus 1. But it's not x, it's z. Z to the k plus 1 power, like that. Times, I also have 1 over k plus 1 factorial. And then I have x minus c, absolute value. So what that's going to give me is the absolute value of 1.6 minus 1 raised to the k plus 1 power, like so. Okay? All right, so let's see what we have here now. The negatives are going to go away because of the absolute value. The k factorial and the k plus 1 factorial are going to reduce, so that all I'm left with in my denominator is k plus 1. Right? That's the factorials are going away there. I'm going to have 0.6 to the k plus 1 power. So 0.6 to the k plus 1 power. And in my denominator here, I still have a z to the k plus 1 power. Okay? Now let's talk about this for a second on the side over here. The z value right here has to be in an interval between x and c, right? Whichever one's greater, lesser, like whatever you can think of. In this case, my x value is 1.6 and my c is 1, right? So I have my x value, I have my c value. So in other words, our z value should exist somewhere between 1 and 1.6. Okay? Now look at the particular setup here, or even over here, either whichever one you're looking at. The z to the k plus 1 is yet again in the denominator like the last one we talked about. So, and it's just to a straight up power, and the power is just going to keep getting bigger. K plus 1, k plus 2, k plus 3, right? This is just going to keep getting bigger. So the larger I let z be in the interval between 1 and 1.6, the larger the denominator is going to be. Okay? That makes this a decreasing fraction the larger z gets. Okay? So as z increases, then error decreases. Right? Error is not a good word for that. As z increases, the derivative value, fk plus 1, decreases. Okay, that's what we can tell from this. So if I want the maximum, okay, the max value of the k plus 1 derivative of z, okay, then that's going to happen when z is 1, because that's the furthest over in the interval that I can get. Okay, that's as far over in the allowed interval of what z can be. So that's going to max out my value if I let z equal 1. Well, that's nice and convenient. If z is 1, then this piece right here is just times 1, which is going to not change anything. So I have a calculation then for my error, this calculation right here. What I now need to solve is the inequality where that error, the 0.6 to the k plus 1 power divided by k plus 1, needs to be less than 0.000000001, like so. The best thing to do for this is to chart it out, then actually try to solve the inequality. Okay, so this is what I mean by charting it out. Okay, because I'm going to solve this inequality, but we don't need a k value that's a decimal. I don't need to know the exact moment that this particular inequality crosses over. I just need a whole number k, because that's all I can do is whole number terms, right? I just need that to know which whole number as soon as I switch from, say, 19 to 20 or something like that. 19 doesn't work, but then 20 does. Okay? So that's why we chart these things out. If I take a particular k value, right? So like 1, 5, 10, let's say. Then the calculation 0.6 to the k plus 1 divided by k plus 1. And let's see what values we get here. Okay, so I've already plugged these in to save a little bit of time. If you plug in 1.6 to the 2 divided by 2 is 0.18. Okay, that's what my error would be calculated out to be less than. Okay, so remember, this thing right here is what my error R is less than. My R sub k of 1.6 is less than this. because we didn't pick the exact z, remember? We picked the maximum z. Once we picked that maximum z, I already set that my error is not equal to this, but it's the less part, the boundary part that we talked about before. But it's less than this, and we're saying that we want this to be less than that. So that'll achieve what we want. It'll guarantee that my actual error is going to be less than that. Okay? So my actual error is less than this. This is the upper boundary. That's still not a good upper boundary for error, though. It's not even a small decimal. Okay? If k is 5, 0.6 to the 6 divided by 6, then I get 0.007776. Not terrible, right? We got some zeros here, which means we've got accuracy at least up to the third decimal place here. Well, second decimal place, I mean. Third one is the first one in question. At 10, when k equals 10, I have 0.000329,816. So we only gained another decimal place of accuracy there with the other 0. So from 10, I went ahead and jumped to 20. And then after that, I started jumping intermittently and plugging things in. I jumped up to 29. Okay, so here we go. For 20, I have 0.000000104. 4, 6, the rest doesn't really matter. And then at 29, I had 0.000000736,913. Okay, so what that means is if k is 29, I actually did 0.6 to the 30 divided by 30, right? And so what we see here is that after I finally get that far, I'm able to say that this is less than this. And yes, I know there's more zeros here, but literally if you go just one back at 28, there was a number here like 3 or 4 or something like that that was bigger than 1. So since they were in the same decimal place, it wasn't technically less. So right here at the 29 is where I can actually say this number right here, the error maximum calculation, is definitely less than the called for accuracy. And this is less than that, so therefore this is the guarantee. So the answer is you need P sub 29 of x, right? Which means n equals 29. Not 29 terms, it's actually 30 terms, right? To approximate that appropriately. Okay? Now, incidentally, the actual value of ln of 1.6, okay? The actual value, well, I say actual, the value I looked up, 0.470003629245744. And of course there's more, okay? If you plug up, I only did a couple of these just to give you an idea. If you plug in P5 of x, then, not of x, of 1.6. P5 of 1.6 is around 0.475152, right? So already you can see that I've only got a couple of decimals there, but then the 5 is way off of 0. So then I also, just to give you an idea, I plugged in P of 11. That's just what I had on me at the time. It was 0.47012, and of course both of these have other, pieces after them. But you can see that's when you start having the 3 decimals of accuracy, like right after the 10, right? It was at P11 here. so on and so on. Okay, so you'd actually have to go down to 29, which means I'd be physically adding 30 terms of the series, and then it would give you something along the lines of the first 8-9 digits of this in there. And technically the calculator can go a little bit further if you find a way to scroll your screen over. Okay, but you can see where this could be a useful technique. Okay, I can actually dictate where my accuracy is and guarantee that you have that much of the accuracy of your approximation. The trick is, for this one, the real method is being able to have that pattern to convert your generic derivative in the formula here into something that you can actually do the calculations with the x's and the n's and the z's there. And then being able to find that maximum value, which z causes the maximum derivative value there. Very often it's one of the endpoints on these things a lot of times because powers of x. But okay, so hopefully you get the idea of how we can approximate the two different ways, bounding it and then choosing accuracy. There are other places in calculus where Taylor series, or just power series in general, can be a useful tool for evaluating things. These two examples that I want to show you here can come up every now and then. Limits and integrals, especially limits and integrals that can't be reduced any other way, or at least not an obvious way. Okay, the hyperbolic cosine of 3x to the 4th minus 1 divided by x to the 8th. Now, you could try rewriting the hyperbolic cosine by its definition. Of course, the hyperbolic cosine, cosh, of some value y, let's say, is e to the y plus e to the negative y over 2. I could start by doing that and trying to do my limit that way. But to be honest with you, if I'm not going to do L'Hopital's rule, which, by the way, this one does fit into that category, because hyperbolic cosine of 0 is 1. I have a 0 over 0. Then my next line of defense here would be, let's try writing it as a Taylor series. Okay? Now, the hyperbolic cosine Taylor series I listed in the last lecture. Pause me real quick and go back and look if you need to. But it's basically the same as the normal cosine, it's just not alternating. It doesn't have the negative 1 to the n in it. Okay? So that means I'll start by doing this. This will be the limit as x goes to 0 of the summation from n equals 0 to infinity of x, quote unquote x, in this case 3x to the 4th, to the 2n divided by 2n factorial. And it's not alternating, whereas normal cosine would have been. The minus 1 is still out there, and my denominator is still x to the 8th. Okay, so what I'm going to do is I'm going to shift this negative 1 up to the front, and I'm going to write out a few of the terms of this. So I have the limit as x goes to 0, negative 1 plus. Now, the first few terms of this. When n equals 0, right? When n equals 0, I'm going to have the 0 power here, which is going to be 1, and 0 factorial, which is 1. So I've got 1. Next, if I were to plug in n equals 1, then I would have 3x to the 4th squared, which would be 9x to the 8th, over 2 times 1 factorial, which is 2. Okay, plus, when n is 2, I'll have 3x to the 4th to the 4th. So that would give me 81 x to the 16 over 2 times 2 is 4. 4 factorial is 24. Plus, okay, so I hope what you're seeing is that I'm going to continue to have more terms. The next one is going to have x to the 24 in it. The one after that, right, x to the 32. It's going up by powers of 8. And that should make sense to you because it's going to be x to the 8n here. Okay? And it'll have some other numbers with it. But look at what's going to happen. Immediately, the plus 1 and minus 1 are going to add to 0 and go away. And then everything else is divided by x to the 8th. So what I have here is the limit as x goes to 0 of 9 over 2 plus 81 x to the 8th over 24 plus something else with x to the 16 x to the 24, so on and so on. Every other term still has some x's left in it because the first one matched x to the 8, x to the 8, right? That wiped out. Everything else just lowered in power but still kept the x's. And I have the limit of letting x go to 0 of this whole thing. So all of these pieces are going to go to 0, and I'm just going to be left with this guy right here, 9/2. So that's my limit value in this case. Okay, so if you have a power series or a Taylor series that lines up just perfectly like that, then your limit can literally just fall apart for you. It's definitely something worth looking into versus doing stage after stage of L'Hopital's rule. Or sometimes L'Hopital's rule doesn't even apply if you don't have that 0 over 0, infinity over infinity, something like that. Okay, the integral of the ln of 1 plus 8x cubed over 5x. Not by any stretch of the imagination an integral that I would like to field on a normal day. And this is just one of many different kinds of integrals that can come up. And if it happens to be an integral that doesn't even have a closed form, those do exist, by the way, it can be a difficult integral or it can be an impossible integral. By impossible, we mean sure there's an answer, but it's not some sort of nice closed function or function string that you could come up with. Okay, there are some integrals out there that simply don't have what we call a closed form answer. And that's where we get some of our special functions like the beta function and the gamma function and the ERF error function for all kinds of other approximation values. This is sort of the start of that field of study. Okay, so one option that I have is to go ahead and make this into some sort of power series, a Taylor series, okay, or Maclaurin series, whichever one it happens to be. And then that's something that I can do the antiderivative of, and then I will have my my approximation of the antiderivative itself. Okay, so I can actually turn this into a series and integrate. So let's do that. I'm going to start by factoring the 1/5 out and rewriting this as x to the -1 here. Okay, now the power series for ln, remember, was, I'm going to use this one, the one centered at 1. It was x minus 1, -1 to the n over n, x minus 1 to the n power, and n goes from 1 to infinity. This is the series that I'm using. Okay? So here, my 1 plus 8x to the third is going to take the place of my x. So I will have summation, n equals 1 to infinity there. I'm going to have my -1 to the n. Oop, that should be a +1 on that one. +1. Over n. And then I have 1 plus 8x to the third minus 1 to the n dx. Okay. So I've plugged everything into being a series. Now let's try to consolidate and simplify this thing. Obviously, plus 1 and minus 1 are going to go away on these two. And then I'll have 8 to the n and x cubed to the n. And then I need to incorporate this other x here. So I have 1/5 integral of the summation from n equals 1 to infinity. I've got -1 to the n plus 1 times 8 to the n all over n. And then I'll have x raised to the 3n minus 1 dx. So I have x to the 3n, because of power to a power you multiply them. And then I've got the extra minus 1 that I'm multiplying into it. And then I also have the 8 to the n that comes out there. Okay, so now this is in a form that I can do an antiderivative, the integral of the x portion here. So then what I'll do is, since I'm actually doing the antiderivative here, I'll go ahead and put c plus, right, for my integration constant. 1/5 times the summation from n equals 1 to infinity. And I have -1 to the n plus 1, 8 to the n, all over n, right? All of that is the same. But now this is the part that needs to get integrated. It's going to go up 1 power, right? I'm actually going to make it increase a power to x to the 3n power, right? So it's times that. But remember, whatever you multiply, you also have to divide by the new power. So then I've actually got a 3n squared in my denominator here. And this is now the series that I can start listing out terms for, right? If something were to ask you, hey, list the first few terms of this, right? You wouldn't count the c as the first few terms, of course, right? And then probably with the 3 right here, I'd count the 1/5 and make this just a 15. It's probably the most concise way to make this thing work here. So yeah, c plus summation n equals 1 to infinity, -1 to the n plus 1, 8 to the n over 15n squared times x to the 3n. So my first term, when n equals 1, right, I'm going to have a positive 8 over 15 x to the 3, right? Plus, when n equals 2, this is going to be odd, so actually this should be minus because it's alternating. Minus, I've got 8 squared, 64, over 15 times 4, which is 60. So 64 60ths, because it's 8 squared and 15 times 4, yeah. X to the 6th. And yeah, of course, we could reduce that. 32 over 15 works as well. Uh, 32 over 30 is what that would be, actually. So then that would be 16 over 15. Much better. X to the 6th, right? Then, of course, plus. And then I'd be doing n equals 3. So then it would be, yeah, it would be positive again. 8 to the 3 power is 512. And then I have 15 times 3 squared, 15 times 9, 90, and 45 is 135. And of course this would be x to the 9th minus dot, dot, dot. You get the idea. So this This would be a Taylor polynomial for the antiderivative, for the solution to this integral. Okay, and of course we would also intend to write it in its closed form like this. Sometimes there are special ones, like I said, that simply don't have a closed form. So this is definitely a worthwhile approach to being able to have a representation of an integral that maybe you can't do, or maybe that's just unattainable at the time. And then sometimes these are ways of actually creating brand new functions. We say that some special function can be the solution to an integral, and then that integral is just not attainable at that time. So I'd like to finish up our conversation on Taylor series by reaching far ahead into your math future and hopefully seeing that you're going to take differential equations. This is a pretty interesting topic, and it actually starts to relate more to your engineering and physics and chemistry, even more than just your plain calculus does. Differential equation just means that you have an equation to solve that already has a derivative in it, right? So basically, one like this, y prime plus 5y equals 0. And what we assume here is that y is equal to some function of x. And that's the solution. In a differential equation, we're just finding a function that when substituted into y, I actually can make that a true equation, a true statement. Okay? So I'm looking for some function that when I take the derivative and add it back to 5 times the original function, that we get it equal to 0. Okay, so one approach here that goes along with what we've been talking about is to use a series, a generic series, and then try to solve for the terms of the series to see if it's a series that you recognize, and then you would then have a way of converting back to the solution at hand, which would be the function that would come from the series. Okay, so here's what we do. We let our function equal some generic summation a sub n x to the n. Now, of course, I could actually center this at some other number. You'll notice I'm centering at 0. Okay? I don't have any preface for any other number because this didn't give me any other information like, oh, I'm interested in the function at 10, like f of 10 is something, or I have f of negative 2 is something. If it had actually given what we call an IVP, an initial value problem, then I would have more of an idea of where I would want to center my series. But we weren't given that. We're just sort of staying kind of generic here. So I'm just going to center it at 0 to make everything come out smoother and nicer. Okay, so that would be what goes into y right here, right? So we'll let that equal y. Okay, if that's true, then y prime is just going to be the derivative of the function. And remember, to take a derivative of a sequence, a series like this, I'm just going to take the derivative of the x portion. And I lose one of my terms in the process. So I'll have a sub n times n x to the n minus 1. Right? That would be my derivative of that particular function series. Well, okay, so now what we'll do is we'll take both of these representations and plug them into the equation to see if we can find a solution to the equation. So I plug the derivative piece in. That's going to be the summation from n equals 1 to infinity of, I'll just do n times a sub n x to the n minus 1 plus 5 times the summation from n equals 0 to infinity. And then I have, right, this a sub n x to the n equals 0. Okay? So then from here what I do is I take this series right here and I want to try and align it with this one so that I can pull out the, not pull out, but like merge the sigmas, right? Sigma is not an actual value here that I can pull out. That's not a good way to look at it. But if they both have the same numbering, right, then I can actually merge the two because all it is adding additions, okay? So for here, first of all, I'm going to bring the 5 in so that it's part of the summation. So I'll have 5a sub n x to the n. And on this one, I'm going to renumber right here. And it doesn't really matter what letter you pick, okay? But let's say I let k equal n minus 1. If I let k equal n minus 1, notice this will be x to the k, which is the same kind of structure as I have here, x to the n. Okay? So I'll have a new summation, k equals n minus 1. 1 minus 1 is 0, and it's still going to go to infinity because you can't subtract 1 from infinity. Okay? But here, instead of n, I'm going to have n plus 1 because k is n minus 1. That means n is k plus 1. Whoops. K plus 1. Also, this will be a sub k plus 1. And then this will be x to the k. Now, I used a different letter there, k, just so that you can see that it is possible to reorganize a summation with different numbers. Notice I'm still going to get the same values, right? When n is 1, this is 1 and a sub 1 and x to the 0. When k is 0, I still get 1, a sub 1, and x to the 0. All of the numberings are the same. I've just symbolized it differently, okay? So for all intents and purposes, k and n in this sense, because this is a different n than that n, okay? But these two summations now are lined up so that I can actually merge them. I can merge them into one big summation, and I'll just use n for, you know, the purposes of this. I could actually use whatever. I could use a or b or d or whatever. It doesn't really matter. The numberings are what matters. Okay? And then I have x to the n, x to the n. Those are the same. X to the k and x to the n, because they're going to be numbered the same. When n is 0, x to the 0. When k is 0, x to the 0. So I'm just going to factor those out. I'll have x to the n, like this. Okay, and then what that tells me is that I have k plus 1, not k, n. N plus 1 times a sub n plus 1 plus 5 a sub n. Okay, now notice what I've done is I've merged the sigmas and I factored out the polynomial portion. Okay, it's actually all the same polynomials. Don't let the different letters throw you off, because it's about the numberings. Okay, x to the 0, x to the 1, x to the 2, 0, 1, 2. That's the same. I factored them all out, and what's happened is I now have just the coefficients here. And so what I have is that this summation is equal to 0. Well, think about this. The only way that I can have an infinite sum of this nature equal to 0 is if each individual term was 0, right? Because it would have to zero out all of the different powers, because otherwise the powers themselves wouldn't combine all the time. Okay? So what this is telling me is that for each value of n, okay, this particular combination has to equal 0 for every value of n. So that gives me an equation to solve. N plus 1, a sub n plus 1, plus 5 a sub n must be equal to 0 for all n. Okay, so then this is a recursive statement. What this means is if I know one of the values, like if I know a sub n, I can use it to calculate the next one, a sub n plus 1. So in that light, what I do is I solve for a sub n plus 1. A sub n plus 1 is going to be negative 5 a sub n divided by n plus 1. What I did was I just subtracted this over and I divided by n plus 1. Okay, so what I have here, like I was saying, is a recursive statement where if I know one term, I can plug it in and get a value for the next term. Okay, so let's write out a list here so that you can get an idea of what's happening here. Okay, so I'm going to start. I'm going to start with A0. Let's let A0 just be some constant, some number. It doesn't really matter what it is. To actually figure out what that is, you would have to have more information, like I said before, like an initial value problem or something. Okay, so let's just call it something like C, right? Not the center, right? I'm not talking about for the series over there. It's just some number, a constant, okay? So then what is A1 going to be? A1 is 0 plus 1. So if I do A0 times negative 5 over 0 plus 1. So that would be negative 5 A0 over 0 plus 1. Well, A0 is just C. So I just get negative 5C. What would A2 be? Well, it would be negative 5 times A1 over 1 plus 1. Right? With me on that? So A2, the next one, right, is based off of A1. Well, A1 is negative 5C. Times negative 5 gives me 25C, and then it's over 2. Okay? So then what would A3 be? Times by negative 5 would give me negative 125C over 2. But then it would be over 2 plus 1. Right? So times 3 again. Okay. Next, A4. If I multiply by negative 5, right, and then divide by 4, because it's going to match the conscript there. Okay, so that's going to give me 625C over the 2 and the 3 were already there. I'm dividing again by 4. Okay, so by now I'm hoping you're seeing a pattern. They're alternating, right? I have positive, negative, positive, negative, positive. Okay, so A sub n, the most generic one, is going to be alternating negative 1 to the n, right? Because 0, 2 is squared, yeah. Okay, and then A sub 4, this is 5 to the 4th power right here. Notice A1, there's 1 5, A2, there's 2 5s, A3, it's 5 to 3. So it's 5 to the n power. Okay? And then in the denominator here, oh, don't forget it's times C, right? Times C. And then in the denominator, notice I'm getting 2, 3, 4, where I had 2, 3 before that, and then I just had 2, and then I just had 1. That's n factorial. Okay? So I was able to get this to a point where I could get some sort of relationship among the sequence terms themselves. Then I could build this list so that I could make the generic term of what A sub n is. Once I build A sub n, guess what? I can plug it back into A sub n here, and then I'll be able to see if I can make a function out of that. So my function, my solution, y, is the function which is defined by this series where I have negative 1 to the n, 5 to the n, c over n factorial times x to the n. Okay, so let me merge some things together here. This would be a summation n equals 0 to infinity of negative 5x all to the n over n factorial. And the c is just a constant. I'm going to pull it out front here. Okay? Now, it may not be as obvious yet, but we had a power series, a Taylor series. If you go back to the last, I showed you a power series that looked like this. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. And lo and behold, notice I have that exact same structure. I have something to the n with an x in it over n factorial exactly. And it's the sum from n equals 0 to infinity, which means that one possible solution, you don't know if there's more or not, there may not be, there may be, would be c, some constant, times e to the negative 5x. And of course the c comes from the constant of integration, if you will. We had a derivative here and we were solving it. Another way would be to solve it more directly, but notice I now have an actual solution to this here, right? That is a function where if I took the derivative, right, I would get negative 5 e to the negative 5x. And so these two would have both the e to the negative 5x. But one would be negative 5, one would be plus 5, and it would actually equal out to 0. So this does actually solve that particular differential equation, okay? This is a rudimentary and sort of hand-waving piece to it, okay? But in differential equations, there are several methods, and this is one of the very viable, important methods that we use to solve a lot of larger differential equations that may not have a solution otherwise, okay? So I hope this lecture has shown you a good light on ways that we can use Taylor series for approximating, for solving, and finding solutions to things that we normally wouldn't have an avenue for.